Welcome to the Types 1 session. So for the first talk, Matthew will tell us about extensible data types with ad-hoc polymorphism. So please go ahead.
All right, thank you very much. So this is work by myself, Yanning, Ara, and Ningning. All right, so extensible data types and type classes are two features of type systems for describing modular code. And these two features have both been studied in a lot of detail in isolation. And the types of modularity that they let us describe are different. So our motivation for this project was a lot of the types of boilerplate code that you often have to write require some powerful modularity. And we are hoping that by combining these two features, we could describe these types of boilerplate code in nice and generic ways. So in this presentation, I'm going to describe the language that we came up with and describe how we fixed some of the problems with the simple approach to combining them, which runs into some issues. Okay, so first I'm going to start off with some background on what extensible data types are, since they're less common than type classes. So say, for example, we have this really simple record type here, which I'm using slightly different syntax for, and we'll see why I'm using that in just a minute. And it has two fields, a min field of type string and an age field of type int. All right, and here's an example of a term of this data type. This is a picture of Yanning's cat here. And let's say, for example, that we want to write a really simple function that operates on this data type. So here, this function takes a pet as input, and it projects out the name field using the / projection operator, and then converts it to uppercase and returns it. So this function works perfectly fine for the purpose that we wrote it for. If we apply it to Amber, then we'll get the result we'd expect. But you'll notice if you look at the body of this function here, that the only thing that it actually requires about the input is that the input needs to have a name field, and that field needs to have type string. And so the annotation of pet here is actually much more restrictive than it needs to be, because it specifies the full set of fields that's present. And if, for example, in our code we had a use case where we wanted to extend pet with some extra fields, or maybe we instead have like an owner class, or sorry, an owner record type that also has a name that we might want to apply this to, well, this function wouldn't work because the annotation is too restrictive. And so we'd have to duplicate the function and give a different annotation. But we could solve this if we could adjust our type to be less restrictive. So essentially what we want to say here is that the input should be any record as long as that record has a name field of type string. And so using extensible data types, we can do this. So this is the first way that we have to adjust our type syntax here. So instead of requiring this pi record syntax to be given all as one thing with a concrete list of fields, we're going to split this up into one piece of syntax that describes some record with fields given by tau here. And this piece of type syntax is going to have kind star. And then we'll have a separate piece of syntax for giving a list of entries. And we'll refer to this as a row. And it has its own specific kind. So by combining these two pieces of syntax together, we can give the definition of pet that we already had before. But the more interesting thing that we can do is we can introduce type variables and use them with the first piece of syntax. And so this lets us state the first part of the type that we wanted for this function, which is that we should have any record as the input. And so here we're being abstract about the fields that our input will have. But this type signature is still incomplete because now it's too general, because we actually need to be able to perform the projection of name in the body. And so to fix this and to restrict our type signature here in the way that we need to, we're going to introduce this extra piece of type syntax. So this less than squiggly is a constraint which says that tau0 and tau1 should both be rows, and the set of entries in tau0 should be a subset of the entries in tau1. And then by using this piece of syntax, as we have on the screen here, we can ensure that this projection of name will be justified. Because however A is instantiated, the fact that this constraint is present will ensure that the name field is there and has the right type. Okay, so that's the first example. Now I want to give a second example so we can see the other type of row constraint that often comes up. So here we have a function that's similar to the previous one, except for instead of just returning the uppercase name, we're going to replace the name that was present in the original input and then return a new pet with that uppercase name. And you'll note here that in the body, instead of just mentioning name, we actually do have to mention the age field here because we're copying it into the output. But this explicit mentioning of that here is really not something that's morally necessary, right? Because really the only thing we're doing is changing the name field. So it would be nice if we could express this in a more modular way also. And so this is the constraint that we need to introduce into our type system in order to do this. So this constraint here means that all three of the taus should be rows again, and the entries in tau 0 when concatenated with the entries in tau 1 should produce the entries in tau 3. And then by using this constraint, we can rewrite the function as follows. So you'll notice here we're quantifying over two different row variables. A here represents all of the entries that are present in our input and output, and B is all of them except for the name field. So now, because this constraint holds, on the term level, we can use this plus plus concatenation operator to combine the record with just the name field here together with P after it's been annotated with the type that just has the fields from B. And this annotation of P here in the body is also justified by the fact that this constraint holds, because if name and B concatenate to A, then we can just discard the name field to convert P to a record of B. Okay, so that's extensible data types in isolation. So now I want to give a really simple example that combines these two features together so we can see the different sorts of modularity that they enable. So here's another really simple function again that's written for pets, and we can make this more modular. First, by doing the thing that we did in the first example, where we get rid of the explicit mention of the pet type, and we replace that with a type variable and add a containment constraint to ensure that the projection of age that we're doing here is justified. And you'll notice that there's a second thing here that we can do to make this more general. So the operator that we're using in the body here on the age fields, the greater than operator, doesn't specifically require that the input should be integers. It allows any type as long as that type has an instance of the ORD type class. And so we can further make this type more modular by replacing the explicit mention of int with a type variable b here, and just requiring that that type variable must implement the ORD type class. And one thing that you'll note here is that the constraint for the containment, as well as the constraint for the type class, appear in the same position syntactically. And this is because in our system, these two constraints are the same sort of thing. They're all just constraints. Okay. So I hope this example shows how the two different sorts of modularity that these features give us are different. Here, row polymorphism is letting us describe a type that's generic over the fields of a record. And we can also use this feature for talking about generic cases of variance, though I won't talk about that too much in this talk. And then type classes here are letting us describe a type that's generic over some group of types that support common operations. In this case, the greater than operator. Okay, so that's one simple example. Now I want to go on to a more complicated example, which is also much more powerful and interesting, I think. So here we have this sort of boilerplate that you might commonly write when dealing with records. So this is an instance of the ORD type class for the pet data type. And what we're doing here is we're going through the fields and comparing each of the corresponding fields in the input. So first the name and then the age. And then at the end here, we look at the result of the first comparison. And if that was EQ, then we're going to fall back to the result of the second comparison for age. But otherwise, we'll prefer the first result. And so this sort of approach to defining ORD is, very straightforward. And it's basically always the same for any instance of ORD that you want to give for a record. And so it would be nice if we could do something to avoid requiring the user to write this manually. And there are features in existing languages that do this. So for example, deriving would automatically generate an instance that would look basically exactly like this. And that works for the ORD type class, but it requires some special work inside the compiler to support this. And so it's not the easiest for users to support deriving for new type classes they might define. So here in this example, we're going to see how we can define a very generic instance of ORD using the combination of these two features in order to make it easier for users to define these sorts of generic things. Okay, so just to summarize, in these sorts of instances, the approach that we're going to take is we're going to iterate through the corresponding fields of the inputs, and then we're going to aggregate the results in some way. All right, so here's the outline of the instance that we want to define. So you'll see here that I've left the implementation on the term level blank, and then also there's a blank here for the prerequisite of the instance. So like I said, the thing that we're going to want to do is go through the fields of these inputs and compare them all. And so in order for that to be possible, we need to actually have the required type classes, in this case ORD, to make that possible. Now, if we were just implementing ORD for a list of A, for example, then writing the prerequisite would be straightforward, because A would just be a type variable for a normal type of kind star. And so the prerequisite would just be ORD A, and then you could compare all the elements in the list. But here, A isn't just a normal type variable, it's a row, because we're using it with this pi syntax here. And what we actually need is for ORD to be satisfied for all of the fields inside that row. And so we're going to have to introduce a new constraint to be able to express the prerequisite that we need here. And that's the all constraint. So the meaning of this constraint is that tau0 should be a type level function that returns a constraint, and tau1 should be a row. And then this constraint will be satisfied when all of the entries in tau1 satisfy tau0. So to give some examples here, if we have all ORD for the row that the pet data type is based on, this would be satisfied because we have instances of ORD for string and for int. But all ORD for this row here with the function type would not be satisfied because there's no instance of ORD for int to int. Okay, so if we take this new piece of syntax and we put it as our prerequisite, then this will give us the guarantee that we need in order to be able to compare all of the fields. So that's the type level stuff handled. But actually, there's a problem that I haven't mentioned so far, which we have to deal with now. So I've been previously talking about how we're going to want to go through the fields and compare them. And we'll start with our first field as having the highest priority, and then we'll fall back through the other fields in case earlier comparisons result in EQ, and so we don't have an exact decision yet. But in order to do that, we're going to want some consistent ordering of what that first field is, right? And we might assume that this is obviously going to be guaranteed, but there's an aspect of extensible data types that I haven't mentioned yet, and that's something called commutativity. So I have two comparisons on the screen here, and you might expect that the first one should result in the result true because A comes before B, but the second should be false because 3 is not less than 2. However, the part of row types that I haven't mentioned yet is that we often consider rows with the same set of entries to be equivalent, even if the entries aren't given in the same order. And the reason for this is that it's really convenient for users, right? If you're projecting things out and concatenating things together, it can be really tedious to ensure that the order always matches up everywhere. And so by having this equivalence, we make things much more convenient. But the issue with this in the context of type classes is that all of these 4 record terms that you see on the screen here can then be given a record type based on either of the 2 rows that are given here in this equivalence relation because of commutativity. And so the issue with this is that the behavior of the code that contains the type class, it depends on how that type class instance gets resolved. But since these terms can be given 2 different types with different rows and different orderings of the entry, we can resolve that instance in 2 different ways, one for each of those types. And in those 2 different resolutions of the type class, different fields will be compared first. And so what this all means basically is that depending on which type we pick for resolution, we can get behavior for either of these 2 comparisons, which gives either result, depending on which field is first, which is obviously a really bad problem because yeah, we have essentially non-determinism here, depending on which type we pick. Okay, so the easiest solution here would just be to say we're going to get rid of commutativity altogether. But that's really not ideal because one, for example, like I mentioned earlier, it's really convenient for users. And second, there's a lot of type classes where the order actually doesn't matter. And so we'd be imposing this restriction for no reason. So for example, the EQ type class, when we go through the fields, right, we'll compare them all for equality, and then we'll aggregate the results by just ANDing all those individual comparisons together. And so since that AND function is like mathematically commutative, it doesn't matter what order we do the aggregation in. And so in that case, we can allow for commutativity, and it doesn't matter which row type is picked for resolution because the behavior will be the same regardless. So the solution that we chose instead was to allow the user to control whether or not commutativity takes place for specific record types. So here we have this piece of view syntax that we introduced, and it can either be N for non-commutative or C for commutative. And then the Pi syntax here has a place that U can be given to specify which of the two cases we should work with for this record. There's one other aspect to this that I'm not going to go into too much detail here, but essentially we can have something called commutativity polymorphism also for functions where either option is allowable, but we want to preserve information about commutativity between input and output. But yeah, I'd recommend reading the paper about that because we don't have time to go into that here. Okay, so now we can finally go back to our instance that we're trying to define. And if we add the N indicator on our record here, then this will resolve our problem for this instance. Oh, okay. So now that we've resolved that problem, we can actually implement the term. And we can do this by introducing a new primitive on the term level. So this primitive int here is short for induction. Essentially in this context, you can think of it as a fold. There is a good reason why it's called induction, but that goes into some details of how the types work that I won't talk about in detail here. So basically, the first argument here is a type argument, which is the row that the fold is going to be performed over. So in this case, we're going through the fields in A, and so we provide that as the first argument. The last argument here is the initial value. So if we're comparing two rows that have no entries, right, the empty rows, then we want to start out with EQ as being our initial result, since those will be equal regardless of what instances of the term it is. And then finally, this second argument here is the most important. This is the folding function. So this will get invoked once for each entry in A. And at each point, the first argument will be the label for the current entry that we're operating on. And the second argument will be the accumulator that we've built up so far. And then in the body of this function here, we're going to call the other helper here that we have at the bottom of the screen, which essentially just looks at the first argument and checks if it's something other than EQ and prefers that if it is, but otherwise it falls back to the second argument. And here is the second argument to fall back. We're going to compare the current fields that we're looking at based on L in X and Y. And yeah, this is the whole instance. And this applies to any record where all of the fields implement the ORD type class. So there's two really important things that I want to point out here. So in the earlier examples that we saw with extensible data types, we always justified the operations that we were performing, such as projections, by the fact that certain constraints held. And so here in the folding function for end, it's going to make sure that there are constraints that are present in the type of that, which justify this projection here by giving a relationship between the row A and the entry with L and some other type corresponding to that name. And so this is what justifies the projections that we're performing out of X and Y here. And then second, so you'll notice we're also performing the comparison on those two results. And this is also justified by the fact that that relationship between A and L holds, as well as the fact that this all constraint holds. So by combining those two pieces of information together, we can infer the fact that the type corresponding to L in the row A implements the ORD type class. And so this justifies the fact that the comparison is allowed in the body here. Okay, so that's the general idea of our system. So to sum things up, basically the naive combination of row types and type classes results in the non-determinism that we saw. And we fix this by introducing different commutativities and a hierarchy within those so that the user can control for exactly the behavior that they want in the cases that they're dealing with. And second, by combining these two features together, we allow for some really powerful new constructs, such as all and end, which we saw in the previous example. And there's lots more in the paper, so I'd recommend reading it if you're interested. We deal with rows that are used to construct variant or sum types. We also have higher-kinded rows and two other constructs for working with rows, lift and split. The semantics of our language are defined by elaboration. So in the paper, we describe our target calculus, which has some interesting properties of its own. And we give the full description of the elaboration that converts from our source to that target. In our artifact, we have proofs in the Lean4 proof assistant that guarantee the properties we want from our elaboration rules and our target. And finally, in the paper, we evaluate our source language using the Brown benchmark for tabular types, which has a bunch of functions that are useful for working with tabular data. And our system is really useful for working with that sort of data. And so we show that we can implement almost all of those functions. That's everything.
All right, thank you. So we have many questions.
Thank you. I have two questions, but should both be quick ones. So the first question is, you have this example where you use all fields so that you ensure that every field in this record is comparable. But what if I have a data type where some of the fields is only some of the fields is comparable, and I want to restrict my comparing operation to this subset of fields? Is that expressible by your, can you compose your constraint language to allow this kind of expressiveness? And the second question is, do you think if I want also parametric polymorphism, does your method scale, or what the possible difficulty you could anticipate? Yeah, thank you.
So maybe I'll start with the first one. That's a very good question. You could think of maybe implementing this instance using a concatenation constraint and just requiring all for one part of that. But the issue with that is if you express it like that without any other details, a valid resolution of that is just to make the part of the concatenation that implements the all of ORD the empty row, and then everything else will just be considered part of the rest of the row. So what you could do instead, though, is you could implement a second function that has to be invoked explicitly, and then you can provide as input some sort of indicator, which specifies the sets of things that you expect to be comparable. And then, you could do what you're describing. And we do have an example in the paper where we do this with EQ. I'd recommend reading that. And in terms of the polymorphism, parametric polymorphism, maybe we could talk about that afterwards. Hello.
Thanks for a nice talk. I guess I have two questions, very naughty of me, as well. But the first one is, this seems very closely related to the work of Garrett Morris and James McKenna.
Yes.
The Rose system.
Yes.
Can you say something about that?
Yeah, so we're building on their work here. I meant to mention that earlier in the talk. But yeah, the presentation of extensible data types that we're using here is based on their 2019 paper.
Great. No, it's really nice to see something practical being built on top of that. The other one is, have you thought much about doing effect typing?
We haven't, no, sorry. Thanks.
Thank you for the interesting talk. I had a question relating to the constraint language and sort of its build-up as you have parametric polymorphism and so on. Have you had experience with whether this produces sort of useful or nice type signatures from a user perspective, or whether they're easy to infer and so on?
Yeah, so So in terms of the like type signatures that this produces, one thing that we have as like context for that is the implementations that we did for this Brown benchmark for table types. And yeah, I'd say that it depends on the function. There are definitely cases where, yeah, it's very straightforward, but there can be cases where it can be a little more convoluted to express exactly what you want there.
Yep, thanks. We have more questions, including online questions. So maybe I'll ask one of the online questions.
Oh, okay.
No, but please set up your computer, the next speaker, and I ask while he's setting up. So there was a question about whether commutativity makes sense for sums, and also about whether you really want to track commutativity or rather the order of traversals.
Sorry, can you repeat that second part?
So the question is, intuitively, instead of commutative or non-commutative products, I would like to think about ordered versus non-ordered traversals with the order given in the type.
Okay, so in terms of the first part, in terms of order for sums, yeah, so the context there is that like while the order annotation is given on the product or sum type, this order annotation really controls like how that row variable gets resolved. And so there's many cases, where like you could have a function that takes a sum as input and returns like a record as the result. And so, yeah, it's still useful to have ordering information with respect to sums there. In terms of the second part, I'm not quite sure if I follow the question, so maybe, yeah, you could follow up on that later.
Answer directly in the Discord channel.
Yeah.
Okay, thank you. Let's thank again the speaker.